Hi everyone, and welcome to our discussion on synoptic scale features. And what we're looking at right now, we're working our way through different types of atmospheres. So this is the second video on the different types of atmospheres. And we left off talking about baroclinic atmospheres. In the previous video we talked about barotropic atmospheres. That's where there's no temperature gradient on a constant pressure chart. In a baroclinic atmosphere, there is a temperature gradient, but there are two special types of baroclinic atmospheres. There is the equivalent barotropic and the pure baroclinic, or just baroclinic. So we're going to spend some time in this video and the next video looking at equivalent barotropic atmospheres. So equivalent barotropic means that there is a temperature gradient on a constant pressure chart. You actually do see a temperature gradient, but those isotherms are parallel to the height contours. So looking at this, you can see that the isotherms are parallel to the contours, and that means that there is no temperature advection. So what we're going to do is look at the types of equivalent barotropic atmospheres that happen in our atmosphere. You'll see these quite frequently, actually. And we're going to start out with cold core systems. And what we mean by cold core, it means the center of the weather system is cold. So the first cold core system we're going to look at is a low pressure system. Now what this means is that we have a low pressure system, and the center of the low has cold air from the surface or just above the surface up through the upper atmosphere. And this is common of weather systems that are very old. Old weather systems that where the cold air has caught up to the warm air, it's occluded, and as a result you have cold air filling the center of the low. So we call these cold core lows stacked lows, or old low pressure systems. And they tend to intensify with height. Let me show you why. So here we have a cold core low in cross section, and it shows the center of the weather system to be cold, and the exterior, the either side of that low pressure system, tends to be warm. So because of the thickness, or the hypsymmetric or hypsymmetric equation, it tells us that because of colder temperatures, the thickness or the distance between pressure surfaces are going to be closer together. So on the outer part of this low pressure system, where the air is warmer, the pressure surfaces are farther apart, and you can see that the heights are higher. Where the air is colder, the pressure distance between the pressure surfaces is closer, and as you go up through the atmosphere, it causes lower and lower heights in the center of this low pressure system. So this is what it looks like in cross section. On a weather chart, this is what it looks like, and you can tell it is a cold core or old low because you see temperatures in the center are colder, -20, and as you move out you can see temperatures are warmer. If you move off to the south and east on this weather chart, you can see temperatures of -11, -16, -15. So that's one way to tell it's a cold core low. Also, another way is watching the weather system over a period of time, and you'll see that cold air start to fill in the center. So with a cold core low, this is an equivalent barotropic atmosphere. You really don't see any temperature advection here. And as a result, these weather systems don't intensify. They just kind of spin and die. Another type of cold core system is a high pressure system, a cold core high. And cold core highs happen here in North Dakota, where we live, all the time. You see cold air coming out of Canada, cold Arctic air outbreak. And you'll see very strong high pressure systems at the surface, but as you go up through the atmosphere, you may actually see a low pressure system aloft. So this is what a cold core high looks like. It looks a lot like a cold core low, except at the surface. At the surface, you'll have relatively higher pressure, but because of the cold air and the thickness between each successive pressure layer. Eventually you get up to the upper atmosphere and there's actually a low on top of the surface high. So with a cold core high, it's cold at the surface, the air density is very high, and you don't see much temperature advection at upper levels. And this is what it looks like in an idealized version of a weather map. 700 millibars, very cold temperatures in the center, and as you move up higher and higher atmosphere, you'll see actually a lower pressure system on top of this high. This is what it looks like on weather charts. Here is a very cold, high pressure system at the surface. I think this is probably in January. This is behind a cold front. And if you look at the upper levels, you won't actually see high pressure in the upper atmosphere. You'll actually see lower pressure in the upper atmosphere. And you can see an L there. It doesn't really show up as a really strong low, but there is relatively lower heights at upper levels in the atmosphere. So those are cold core systems, and those are equivalent barotropic. In our next video, we're going to talk about warm core systems, and those are also equivalent barotropic.